Hi, this is Mrs. Often, and I'm here to talk to you today about exponential functions. You see that I have two parent function graphs here on my board. I have the green graph and I have the blue graph. Both of them have the same formula associated with them. Y equals b to the x power. However, the green graph is used when that value of b is greater than 1. You can see that it starts off slowly, it crosses a critical point at 0, 1, and then it just shoots off into space. The second graph, y equals b to the x, represents the graph when b is in between 0 and 1. I do want to point out, if b is equal to 1, this graph is really boring. It's just a horizontal line because 1 raised to any power is still 1. So b is not going to be equal to 1. You'll note the domain and the range for both graphs are the same because we can raise a number to any power even if that power is an irrational number or a rational number or a negative number. And you'll notice that these graphs have been reflected in the y-axis. So those are the two types of graphs we're going to be looking at today. And we're going to focus on shifts of exponential functions. Here's the most general looking form of that exponential function. G of x equals a times b raised to the power x minus h plus k. For this graph, the critical point, which on the parent function is 0, 1, is at the point h, comma, a plus k. This graph has a horizontal asymptote, which you should sketch first when drawing the sketch of a graph. That horizontal asymptote is at the line y equals k. Now the default, if k is equal to 0, and we wouldn't see it here then, would be y equals 0. So the x-axis would operate as a horizontal asymptote. And as with all of our other function transformations, if the value of a is less than 0, the graph is upside down. So these are some things when you look at your first exponential functions, you should first be determining where's my critical point, where's my horizontal asymptote, and is my graph opening up or down? Does it go like this or does it go like this? So we're going to do a few examples of this exponential function shift. Here's my function. G of x equals 3 times the quantity 2 to the x minus 1 power plus 1. Now, my critical point is at h, comma, a plus k, and you can see that I have h is 1, and a plus k, 3 plus 1. If you don't believe me that this is the critical point on the function, please stop now and evaluate this expression when x equals 1. I'm going to make a table of values really quickly, but I want you to also check that my work is correct as I make this table of values. So don't be afraid to stop the video and check all that work. My horizontal asymptote here is at y equals 1, and that's because my k value is 1. So I'm going to first draw that horizontal asymptote. Remember, the graph will not cross this horizontal asymptote. Okay, now I have this point 1, 4 here. I'm going to just plug in a few extra values of x. You can pick any numbers you like. I like to pick whole numbers and natural numbers as much as possible. If not, then I pick integers. So when x is equal to 0, I have 3 times 2 to the negative 1 power plus 1 to the negative 1 is 1/2. So I have 3 times 1, 3 times 1/2, 1.5, plus 1 is 2.5. If x is 2, Then I have 3 times 2 to the first, or 6, plus 1 is 7. And if x equals 3, then I have 3 times 2 to the second power, plus 1, and that's going to be 13. So my points here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 0, 1, 2, 3. So you can see at 0, I'm at 2.5, right about here. At 1, my graph is at 4. At 2, my graph is up 3 more at 7. And at 3, it's all the way up here at 13. So I want to join these points with a smooth curve. And to make sure that it looks like the parent function, my line is going to go down and get as close as possible to that horizontal asymptote without touching it. Don't cross the horizontal asymptote. Remember, it's like the third rail on the T. Don't touch it. So that's what my graph looks like. You can see that I've used this table identifying the critical point and finding the horizontal asymptote first. Here's another example. In this example, A is negative. So right away, I'm saying this graph is going to go like this, be pointing upside down. Okay, my H value is -2, K is +3. My critical point is therefore -2, 2. So I'll be evaluating a few more points. I'll do -3, -1, and 0 in order to have a nice selection of points for my graph. Also, my horizontal axis, or I'm sorry, my horizontal asymptote is at y equals +3. So I will draw that in right away. Tells me that all of the action on this graph is going to be happening below this line. So first, if I evaluate with x equals -3, I have -1 times 3 to the -1 power. So that's -1/3 plus 3 is going to be 2 2/3, or about 2.7. If I use -1, then I'm going to have -1 times 3 to the first power, or -3 plus 3 is 0. Then 0, I have 3 to the second power, that's 9. And so -9 plus 3 is going to be -6. And you see this overall pattern of the exponential function. It is getting smaller because it's negative for the a value. And after I pass this critical point, there's kind of a shift in how quickly the function's rate of growth changes. So I'll start plotting these. There's 3, 2 2/3, -2, 2, -1, 0, and here's 0, -6. And again, you see when b is greater than 1, we have that steep drop-off or steep rise after the critical point, much flatter on the other side of the critical point.
Have a good summer, Miss Austin.
Thank you. On our final example, example 3, I have 2 times 1/2 to the x power plus 1. And again, my critical point is at h. Nothing is being added or subtracted to x, so that's 0. Then a plus k is 3. So my critical point is 0, 3. My horizontal asymptote is that k value, y equals 1. So again, plotting that. Okay, not so horizontal on the horizontal asymptote there. I'm going to substitute in -1 for x and then 1 and 2. You notice I have some extra boxes here. If you want to feel more confident about the shape of your graph, I encourage you to use extra points. I think 4 is enough. So I'll start with -1. 1/2 to the -1 power is actually equal to 2. So 2 times 2 is 4 plus 1 is 5. Then 1/2 to the first power, substituting 1 for x, is just 1/2. 2 times 1/2 is 1, plus 1 is 2. And then substituting 2 for x, 1/2 squared is 1/4. 2 times 1/4 is 1/2. So my value here is going to be 1.5. So drawing the graph of my function, I'll have -5 and 3, 2, and here 1.5. And I didn't quite make it through all of those points. But you can see the general shape of the graph. Now instead of going up like this, as happened when b was greater than 1, this has gone downward. Okay, this is an example of what's called exponential decay. So our key takeaways here: critical point, horizontal asymptote, and use a table. Check back with your parent function to make sure that your graph looks correct. And that's how you graph exponential functions. All right. Hi, this is Mrs. Often, and I'm here today to talk about the introduction to logarithms. So let's say that I have this equation, 27 to the x power equals 9. And I need to figure out what value of x will make this equation true. Well, if I want to determine that exact value of x, I need an inverse operation.